Hello and welcome to Podcast.init, the podcast about Python and the people who make it great. You can subscribe to our show on iTunes, Stitcher, or TuneIn Radio, or add our RSS feed to your podcatcher of choice. You can also follow us on Twitter or Google+, and please give us feedback. You can leave a review on iTunes to help other people find the show, send us a tweet or an email, leave us a message on Google+, or our show notes, and you can also join our community. Visit discourse.pythonpodcast.com for your opportunity to find out about upcoming guests, suggest questions, and propose show ideas. I would like to thank everyone who has donated to the show. Your contributions help us make the show sustainable. For details on how to support the show, you can visit our site at pythonpodcast.com. Linode is sponsoring us this week. You can check them out at linode.com/podcastinit and get a $20 credit to try out their fast and reliable Linux virtual servers for your next project. I would also like to thank Hired, a job marketplace for developers and designers, for sponsoring this episode of Podcast.init. Use the link hired.com/podcastinit to double your signing bonus. Your hosts as usual are Tobias, Macey, and Patti, and today we're interviewing Ruth Chabay and Bruce Sherwood about their work on VPython. So could you each introduce yourselves, please? How about you first, Ruth?
Hi, I'm Ruth Chabay. I'm a professor emerita of physics at North Carolina State University. I'm particularly interested in integrating computational modeling into all of the science and technological curriculum at the undergraduate level, especially physics, since that's my field, and that's how I got involved with Python.
My name is Bruce Sherwood. I'm professor emeritus from North Carolina State University. I share Ruth's interests. Together, we've developed a curriculum for the introductory physics course, and we'll have more to say about that. That includes computation. Both of us have been involved with computers for many decades, and we look forward to talking with you all.
So how did you folks get introduced to Python?
We were at Carnegie Mellon in the 1990s, and it was, I think, just in the air there. There was a lot of interest in it. For example, Randy Pausch's Alice project, where students got to import models, fancy models, and do animations, was based on Python. We loved it because of its clean structure, its gentle learning curve, and decided it was a really good first programming language. And its modular structure meant that it was easily extendable, so we could add modules that did what we needed to do.
And so you mentioned that you created VPython. So what is VPython, and how did you guys get that started?
Well, VPython stands for Visual plus Python. That is Python plus a module which was called Visual. And it's an environment that lets ordinary mortals generate navigable, real-time 3D animations as a side effect of computational models. And it's also included in the original classic package was a modified version of IDLE. And it was originally the idea of David Scherer when he was an undergraduate at Carnegie Mellon. He had been in our introductory physics course where Ruth had introduced some computational modeling, and he saw a way to do it in 3D, which sounded very exciting. And he chose Python as the foundation because of its extensibility, its object orientation, its simplicity, its clarity. During the spring semester of 2000, he and we worked together to design what became VPython. He did all of the coding, all the implementation. We spent most of every day together thinking through the design, how to make it work well for people who may not have ever written a computer program before, but were being asked to generate programs that made 3D animations.
So what problems inspired you to create VPython?
It really was originally a side effect of trying to bring introductory physics courses into the 21st century, which is harder than it sounds. Most introductory physics courses are completely happy to stop around 1860 or sometimes even 1700. So most introductory physics courses don't admit that the 20th century ever happened. A part of that was introducing computational modeling so that students would have a chance to see fundamental physics principles in action and to explore the range of possible behavior instead of settling for the two problems that are easily solvable with introductory calculus, so constant acceleration or simple harmonic motion. A problem with that, though, is that most college freshmen, Carnegie Mellon was an exception, but most college freshmen actually have essentially no programming experience. They're really good with computers, but they've almost never written a program. So if we wanted them to actually write models themselves without any black boxes, we needed a language, that environment that was clean, that was easy to learn, and that we could make look very much like the algebraic expressions that we're using on paper. We also really felt strongly that we needed interactive 3D animations so students could observe how their models behave, observe the behavior of the system. You could see planets going around stars, or you could see springs oscillating in weird patterns, and not just look at graphs.
Have you noticed that the students are more engaged after introducing this tool to the classroom than they were prior to being able to interact more viscerally with the principles that they're trying to understand in the physics course?
I think it really depends on the students and the context. Some of them absolutely are. Others see it as an extra burden of something else to learn until they do something that's really cool. And if they see a really interesting, strange orbit involving 3 objects, which is something they never could calculate by hand, or if they see their mass on a spring going around in strange wobbly circles, then they start to get interested.
That's really very cool. I know I certainly would have probably been much more motivated to struggle through intro to physics than I was if there had been something like this involved. So I can definitely see myself finding more motivation, more sort of connection with the material. I think what you said about, your standard intro to physics course stopping in the 1700s is totally fascinating. And I sort of wonder sometimes about that aspect of academics, like how many other subjects are there where even just sort of conceptualizing things in a different way would really help students connect with them better?
It's an interesting question. One of the things that our students can do is make computational models not only of big macroscopic systems, but actually on the microscopic level. They can connect masses and springs and model solid objects, which are actually modeled in many ways very well as a network of masses and springs. So they can actually see and sort of experience how things react at a microscopic level. For example, if you put a heavy book on a table, it looks like the table's not changing, so how can it be exerting an upward force? But you can actually see the network of balls and springs that comprise the solid table being compressed by the weight of the book, if you can model it at the microscopic level. So there are a lot of different kinds of insights you can get from thinking about things this way, and from using computational technology to support making and exploring these physical models.
As you were saying earlier, the fact that there is this extra tool that you're introducing into the classroom at the same time as all of these new physical and mathematical principles, how do you design an API that allows for such powerful 3D visualization while still making it accessible to students who are tackling those new concepts in mathematics and physics so that they don't get overwhelmed by the tool?
Well, that's an important question, and it's a big issue because, of course, students have a lot to learn anyway, and so overloading them is a really bad idea. A lot of care did go into the design of the API. And one of the most important things are intelligent defaults. If you've done any work in 3D and any kind of 3D system, you may realize that the most common thing that happens is you get a black screen because you've forgotten to point lights at the object, or the camera's pointing in completely the wrong direction, or something like that. So it's frustrating. So VPython starts out making sure that you will see any object you create, and if you don't specify any special parameters, it'll occur in some default location and be lit, and the camera will point at it. And that's helpful. There's the syntax, like all Python syntax, is very clean. We don't have to contend with missing semicolons or unmatched curly braces, which is also a big help. And in VPython, the students can actually do vector. It supports vector algebra, so you can do vector algebra as you would on paper by adding vectors and operator overloading make that possible, of course. So what they write in code matches to a significant extent what they would write algebraically on paper. So the translation is a little less complicated. I have to say, though, that it's not just the API. You actually need to surround it with a curriculum and not overwhelm students to start out with. So it's really important to stress a very, very small number of key computational concepts that'll let you do what you need to do, and then introduce them slowly, step by step, in the context of physics activities, so that students get a chance to master them a little bit at a time, instead of telling them to go off and model the solar system as their first homework assignment.
In fact, just today, we got an email from a colleague at a liberal arts college who said, "Oh, it's going so much better this year. In the past," he's new there, colleagues there had developed materials, curriculum materials, that way overloaded the student. There was way too much stuff. And the kinder, gentler curriculum materials we've provided, together with this nice API, makes a huge difference. So the details do matter.
And we've had 15 years of experience refining this approach. So it's
And Ruth and her graduate students at NC State did a lot of work to make those curriculum materials better and more workable. And I have to quote Ruth on one thing. Ruth had the wonderful saying, "Every brace is an opportunity for an error."
I love that. I think that's very true. And as any of us who started up, learning how to program with something like Java, or even, worse, something like C or Perl or something like that, we've felt that pain.
indeed, and still do in JavaScript and other languages.
So I know many schools have embraced the open curriculum idea. Have any of your physics courses using VPython been made available to the non-matriculating public?
In fact, a colleague of ours, Mike Schatz at Georgia Tech, ran through Coursera a MOOC that was an introductory physics course that used our materials and also had used VPython. And they had the students doing significant modeling projects, some of which would involve students going out with their cell phones and taking a video of some motion and then coming back and digitizing it with Tracker and then writing a VPython program to model the motion and try to unravel it.
And it was like 10,000 students.
Well, yes. Like all these MOOCs, it started out with many thousands of students. But the students were pretty enthusiastic about it, and some of the videos they made reporting on their projects were really very impressive. So that ran for a couple semesters, and I think was a very successful thing.
Very cool. I hope we can get. I think I found it, but just in case I didn't, I'll pass it your way, and hopefully we can get the verified link in our show notes, because I think that would be really neat for people to take a look at.
But I think it's no longer running.
I don't think it's running at the moment, but
it required way too much work.
Well, every MOOC requires a lot of work from the instructor. But I don't know if it's going to be offered again. But it did happen, and it was a pretty good experience, I think.
So how does VPython perform its rendering, and if you were to re-implement it, would you do anything differently?
Well, that is a timely question, because as we wrote to you earlier, there's a group of us who are deeply involved in the process of restructuring what was the classic version of VPython for a bunch of reasons. What we're calling classic VPython, which started in 2000, and is still in use quite widely around the world, used OpenGL, CPU-based, did not exploit the GPU, certainly could not exploit the modern browser. So essentially all we were asking the graphics card to do was to draw triangles. It just didn't exploit modern hardware nor modern software, namely the browser environment. So what we're engaged in doing, in a way, we're 0.87% of the way there, 87%, is two implementations of the VPython syntax that will supersede the classic version. One is called GlowScript VPython, available at glowscript.org. That's GLOW script.org. And the other is Jupyter VPython, which runs in a Jupyter notebook in the IPython architecture. And the GlowScript version, to run in a browser where your program is both compiled and executed in the browser, not on the server, which just sends you libraries. The GlowScript version is possible because of the RapidScript compiler, or transpiler, that will go from Python to JavaScript, the language of the browser. And that plus GPU code does what it needs to do. It's necessarily limited in terms of the Python ecology because you can't import an arbitrary Python module. And so, but this is a very suitable environment for beginners, for the introductory physics course in our case. And then there is the Jupyter version. Jupyter notebooks are now increasingly popular among professional computer people. Computer scientists, computational science really love that environment. And so that's sort of the professional choice. We don't consider it to be a very good place to put a novice student who's never programmed before, because it is a sophisticated environment. So we're in the process now of rethinking the implementation and having these two kinds, one for the novice, the casual programmer, and one for the professional.
Both of those environments, the new ones, use the GlowScript rendering engine, which makes very good use of GPUs and graphics cards, which have improved a lot since 2000, so that it's possible to do pretty sophisticated rendering. We can write vertex shaders and fragment shaders and have a lot of that. The computational load of the rendering is almost all done by the GPUs. And that's a big win. And that's possible in the browsers using WebGL, which is moderately new, but allows one to access the capabilities of the graphics card within the browser context.
And for example, we're able to do pixel level correct transparency, which is not easy to do, and it's essentially impossible with a CPU-based renderer like the standard OpenGL.
Well, that's the old OpenGL. The new OpenGL will do that.
Well, only if you use GPUs.
Yeah.
I think that's really great. I know WebGL for a very long time was really heavily browser dependent, and like you'd see a WebGL demo and it would say requires Chrome or Firefox of this or that version to run. Has it gotten better such that you can actually write and publish a WebGL based application and have it work with reasonable degree of certainty on most of the major browsers?
All of the browsers now support it, including Edge. Everybody does.
But that's a recent thing. It's really in the past year or so almost that all the browsers have stepped up and now really do support WebGL.
And in the Jupyter case, when you run your Python program on typically a local server, it could be remote, but typically a local server, you run your standard Python program, then the output is piped over to a browser of your choice, which is where the Jupyter notebook is rendered with its cells of code, images, equations, whatever. But now also a VPython rendering there using the GlowScript GPU renderer so that you have 3D animations, navigable 3D animations as a cell in a Jupyter notebook.
And you were mentioning that your newer versions include vertex shading and pixel level transparency. So is that something that you've had to develop? Have you had to hand develop that specifically, or are you using libraries for being able to do those graphical computations?
No, we wrote the shaders. We're doing some things that aren't entirely standard with using the GPU, and it was essential that we write our own.
And is that a difficult undertaking, or is it something that's fairly standard and low requirement? Personally, I've never done anything like that, so it sounds pretty difficult, but
Well, the learning curve is steep, okay? So you have to learn the shader language, and you have to have a model. You have to learn a model of how the GPU actually works, including some hardware operations that you don't have control over. And so there's a fair amount to learn, but once you learn it, then it's not that bad. You learn a new language. You spend a lot of time thinking about geometry, really a lot of time thinking about geometry, and you have to think about the GPU hardware. But it was kind of interesting. It's not something one would ask a student to do, however.
So one of the remarkable points about VPython is the fact that it does have the ability to execute the simulations in the browser environment, like you mentioned. So I'm wondering if you can dig a little deeper into the technologies that are involved there to make that work.
Sure. The key thing is that the GlowScript piece of this, which is also exploited in the Jupyter Notebook, it's all JavaScript code plus the GLSL language for writing the vertex and
fragment
shaders, and the communication between them. Basically, the structure is this. There are a bunch of so-called primitives: box, sphere, ring, cone, etc. When the program starts up, there are stored into GPU memory so-called models for each of those things. That is, the data that says a box has these 8 vertexes. There are normals to the faces. Here are the triangles that are going to be drawn by the GPU, because that's what it draws, is triangles. And so those are the generic structures, the generic description of your Platonic ideal of a cube. And then in your user program, you say box, left parens, right parens. And what that does is make an instance of the box class. And at render time, the data corresponding to that instance is all that's sent to the GPU, which then refers to the model of a cube and performs things like stretching it to not be cube, changing the color, rotating it in some position, locating it in 3D space with a projection in 2D onto your screen. All that happens in the shaders, in the GPU. The amount of data for one instance of a box or any of these other models is quite small. It's 5 4 vectors of float 64s for a total of only 160 bytes. So you have a very large number of instances of box objects, and all you're sending to the GPU each time you go to render is these 160 byte quantities. The rendering is done about 60 times a second so that you have good looking animation. Obviously, if you really load down with lots and lots of computation, that frame rate will necessarily suffer. But computation and rendering alternate. The way we're able to use Python, which doesn't run in a browser, is, as I mentioned earlier, there's a rapid script transpiler, which will convert Python to JavaScript and then compile the JavaScript. And all of that is actually done in the browser. The compiler is written in JavaScript. It's not exactly perfect Python. For example, the creators, the main creator is Alexander Tsepkov, reasoned that while in Python division by 0 throws an error, and division by 0 JavaScript just produces an infinity, if you were to try to mimic Python exactly, you would have to put in tests on every division operation to see whether the divisor was 0 or not. And that's just a simple example of a more general principle. So there are many projects attempting to transpile Python to JavaScript, but RabbitScript has this particular goal of saying, we're going to do a pretty good job of mimicking Python, but it won't be absolutely correct at the bit level. So,
but it will be fast.
And it'll be fast. In fact, basically, these programs are just as fast as a native JavaScript program. I don't see any difference in the VPython programs running in the browser and the JavaScript ones. Now, in the Jupyter case, the situation is rather different. Typically, you've got a local a local server running on your system, where you're running true Python, true standard Python with full access to the huge ecology of Python modules. The server communicates with the browser, very similar to you going to google.com and there's a server and it sends stuff to your browser and displays it. Well, in this case, this local server sends stuff to a local browser on your machine. And what does it send? Well, in the simplest case, if you write print 3 plus 5, it sends an 8 over there. It shows up in the notebook that you're running in the browser. And its notebook looks sort of like a Mathematica notebook or a Sage notebook, that kind of a thing. And what John Cody invented was that he did two very interesting things. He wrote a pure Python version implementation of the VPython API. Now that means that it's not as fast as the original classic C++ code, but it's fast enough to get going. And we hope later on, when we get most of the API done, is to go look and using Python or other tool to speed up the hotspots. But already the performance is pretty decent. So that was one thing he did, that was really good. The second thing he did was he mastered the Jupyter Notebook environment and figured out how to send this output of changes to this box. Okay, you change the position. So he sends that change information over to the browser. He has a JavaScript program that picks up that data and calls the GlowScript libraries to change the position attribute of this box instance. And the net effect is that the box on your screen moved. And so the chain is Python in a server, a JavaScript program running in a browser, calling upon the GlowScript libraries with their GPU usage to actually make the presentation in a notebook cell. And the performance is actually quite good.
Yeah, so given the real-time rendering capabilities in VPython, like you said, performance is a pretty big concern for the project. And you mentioned some of the ways in which you're tackling that. I'm wondering if there are any other techniques that you have implemented or are planning to implement that will help ensure an appropriate level of speed. And I'm wondering also if the cross-platform nature of the package poses any additional challenges to that work.
Well, given that you're running in a browser, the cross-platform problem is much simpler than it was 16 years ago when you needed very specific code to do graphics on all the different platforms. That was hard. A lot of the cross-platform stuff is now taken care of by browsers, which have to be sure to run on all platforms. And since there is now WebGL support in all the major browsers, that's made the cross-platform problem almost, not quite, but almost a non-problem.
And in fact, the GlowScript versions actually run in mobile devices. You can actually write and run VPython programs on your smartphone. I didn't expect to live long enough to see that.
So our students can take their phones home and show their parents what they did in physics class, which is sort of cool. The original classic was written in C++ for speed, and we're just not doing that anymore. That's too challenging, and that ends up being very platform dependent. You need a binary for every platform. In the GlowScript VPython environment, the almost Python environment, since we're going down to JavaScript, JavaScript is pretty fast. And I think this is a moving target. Stay tuned. Maybe WebAssembly will be even faster or something. But the performance is typically good enough.
In fact, I'll interject that in pure Python, for loops have a large overhead, and so it's important to vectorize things and use NumPy. Our experience so far in the browser world, in the GlowScript version of VPython, is that because the JavaScript for loops don't have a high overhead, we actually sort of don't need NumPy for that most basic reason for using NumPy. JavaScript is actually a pretty fast language.
In the Jupyter environment, which is still really in beta, although it's usable by anyone who wants to try it, the performance isn't bad, actually. It's surprisingly good for having the basic implementation of the core API in pure Python. But
and the communications.
Yeah, and then all the communications using JSON strings between Python and JavaScript. So it's sort of miraculous that it runs as well as it does, in my opinion. But it's not bad. But we will, once we get everything about the API nailed down, then the next project is to start looking at how we could speed it up. And it's possible that Python will help us in some key areas, maybe making vector operations Pythonized or whatnot. But it's actually usable now. In fact, colleagues, including both instructors and professional physics researchers, are actually using this beta environment very happily.
How does collision detection work in VPython, and does it handle more complex assemblies of component objects?
Basically, there is no collision detection built into VPython. In fact, there's no physics built into VPython. It's basically a neutral platform. What it does know is it knows about vectors. It can add and subtract them. It can multiply them by constants, divide them by constants. There's a whole bunch of vector methods for taking dot products, cross products, all that kind of stuff is built in. And with operator overloaded, you could say A plus B instead of A dot add left parens, B right parens. So it's good at facilitating your vector calculations. You can actually do vector calculations with vectors, which, by the way, is kind of a first for physics students, because although vectors ostensibly play a big role, this is the first environment where students, or faculty for that matter, have been able to use vectors as vectors rather than separately as components. I digress. So then there's no physics built in either. Our students are experiencing no black boxes. They are actually writing the physics calculations themselves. And if they want to detect collisions, they're going to have to look at the distance between the centers of two spheres and see if that distance is less than the diameter of these spheres and do something if they need to do that. So it's not a physics engine. You could certainly you could import a physics engine to do this stuff, but in the educational sphere, that's not what we're after. And we didn't want to build into VPython anything other than this sort of minimal capability of being able to render things in 3D, to be able to navigate through the scene, and to be able to do it with vector calculations.
That's really interesting. I guess I had just assumed, because of what I was seeing, the kinds of simulations that I was seeing, that VPython had some kind of object boundary detection and collision detection built in. But in a sense, I can see what you're saying. Not having that built in means that it's wide open for even more sort of flexibility and more broadly, more types of applications can be built with it.
Yeah, there aren't any constraints, so that you could do various things, but the goal was to make a general purpose programming environment that knew about living in a three-dimensional world and could really enable the user to use vectors which describe living in 3 dimensions easily and fluently, and then let the user build the models.
And in fact, in a certain sense, it's neutral. You can use it for whatever you want to use it for. Maybe you want to use it to render something that a physics engine calculates for you, or maybe you want to use it to present chemistry molecules as balls and sticks.
Or maybe you're doing topology or something. it's
an engine, but not a physics engine. It's a rendering engine.
That's great. It just struck me as you folks were talking about this, given that my sort of conception of VPython was a little bit off kilter, it occurred to me, has anyone used it in the sort of genre of creating 3D computational art?
There's certainly things people do that are very beautiful. We don't know everything that everybody does. We know that there have been, hundreds of thousands of downloads, but we don't know what people are doing with it.
Right. I think that's becoming a theme for me. We've certainly discussed it in a couple of other podcasts. For all of us who use open source software every day, take some time to send some love back to your project maintainers, even if it's just a note saying, "Hey, I built this cool thing," or even, "Hey, I really love your project." I think we all sort of owe that to this amazing ecosystem, on whose the individual project maintainers whose shoulders we build things on every day. So, can you talk a little bit about VPython's design and perhaps walk us through how a simple scene is rendered, say the result of the sphere call?
Why don't you first say something about the design principles, and I'll follow a box through the system.
Well, one of the things we wanted, so as I alluded to earlier, one of the things we thought was important was to make it easy for the programmer to create an object of the shape and size and surface properties and whatever that they actually want at the right location, and to make that very easy to do. The first piece is just not requiring them to do that at all. So if you just said box or sphere with no arguments at all, you'd get a box or a sphere at the origin with size of 1 and lights pointing at it and a camera pointing at it. So that part would be easy. But then make it easy to specify other parameters. So different length and width and height for a box, an axis pointing in some direction or whatnot. And those look like standard Python objects with standard Python attribute syntax. So you say box axis equals vector 3, 1, minus 1 or something like that to specify it.
So let's follow a box through the system. Suppose you've written this gigantic program that consists of box, left parens, right parens. And we're going to take the GlowScript version of VPython just for concreteness. And because the Jupyter version is just an extension of using this machinery. So as we said earlier, on setup we get the model of a box and sphere and so on over the GPU memory, so that thereafter we can just give instance information. The instance information for the box or the sphere or the cone or the pyramid or the whatever involves the following attributes: a position, which is a 3D vector, a color, which is actually a 3D vector also, a size, length, width, height as a 3D vector, an axis, again a 3D vector about the direction. The default is 1, 0, 0, namely x direction, but you can have it be something else. How shiny it should be, what its opacity should be, and by default, and you can also specify a texture and even a bump map to go with the texture. So this is this package of 160 bytes that represents that instance of the class box, which is what was made. You made box left parens, right parens. But as Ruth said, having created this object box, that causes the GlowScript machinery also to create a WebGL canvas and display it in the browser, and then put the box in that scene with the camera pointed in the right direction and right distance away, so that the box sort of fills the canvas. And it also turns on mouse interactions to let you rotate and zoom the camera to look at the scene from different places and all. So one way of saying this is, and the cube will be white. It'll be oriented along the x-axis. All these things by default, because when we said box, left parens, right parens, we didn't say anything else in that constructor. We could have included in there, for example, color equals cyan, or length equals 5 instead of 1. But so very intelligent defaults. You get something going with almost nothing, just this 1, 2, 3, 4, 5 character program. Now, that's not the interesting part in some ways, because what's really cool is let's say you write a while loop, and that's, we teach our students at the intro level one way to make a loop, namely a while loop. And it's typically while true, because it has an infinite loop, actually. And the next statement in that while loop is typically rate 50. Don't do more than 50 iterations of this loop per second, because you have to control the speed of the animation to be independent of how fast your particular computer happens to be. And then what you might have as your next statement is, let's say the program actually said ball equals box. And by default, its initial position will be 0, 0, 0, the origin at the center of the canvas. If in your loop you write box.pos, which is ball, the instance of the boxcast, ball.pos equals ball.pos plus a vector that might be a short displacement in the northwest direction. And now you run this program, and I've described the whole program. While true, rate 50, ball.position equals the existing ball.position plus a vector of -1, 1, 0. If you run that program, what you'll see is the box moving off in the northwest direction. Even though in that loop there are no obvious graphic statements at all. You're just recalculating the position of this object. But that raise statement not only clamps the execution to no more than 50 iterations per second, but when the time comes right, every 60th of a second, it drives the GPU machinery to make a new display on the canvas using the current attributes of the objects, in this case, a box named ball.
I think Bruce lives in an alternate reality where
all balls are cubic.
Yeah, balls are cubic.
Okay? So VPython doesn't care. It'll let you call a sphere, call a cube a ball. So the effect is you get an animation, a 3D animation, with no obvious graphic statements there at all. I mean, compare with what you do in 3JS or something, and it's just on a scale different. So it's literally the case that your physics calculations, your calculations of repeated changes to the position attribute of the ball instance of the box class will give you a 3D animation that's navigable with mouse controls. And that was David Scherer's great insight. He was and is an extremely powerful programmer, but he was interested in the problem of how could you make 3D animation programming accessible to ordinary mortals. And his ingenious solution was, do it for them. Make it be a side effect. If they change the position, we should show the position, we should show the thing in a different place. So it's very cool.
Under the hood, there's a fair amount going on. Suppose you have a scene with 100 different boxes in them at different locations, and they're all rotating or bouncing up and down or something like that. 60 times a second, the scene gets re-rendered. And in each case, because you have this model of a cube, a box, is stored in the GPU, what the vertex shader does is say, oh, I see that this object is an instance of this model. So all I'll do is I'll take this model and I'll just do transformations to locate its center at the right place and orient its axis off in the right direction, and maybe stretch it if it's larger or compress it if it's smaller. But that calculation is all done by the GPU, by the vertex shader in the GPU. And it says, okay, given where the camera is, exactly what would you be seeing of this box on the screen? Is it completely hidden? Or are you going to see one corner? Or are you going to see the whole thing at what angle? And
is it transparent?
Yeah. The fragment shader goes, well, now I have to worry about where the lights are, and if it's transparent, what's behind it that I'm going to see, and what color it is, and maybe there's a texture on it. But all of that stuff is all of that really computational intensive stuff is now done in the GPU, which is really good at it and does a lot of it in parallel. So it's doing this computation pixel by pixel, but lots of them at once, which is why it can be fast.
And in fact, in terms of performance, it's sort of a special case in a way, but I took it as a challenge. I had something like 10,000 boxes all swirling around. It was slightly a trick. One of the interesting objects is a compound object, where you take a bunch of objects in a list and you compound them. And now you can treat it as one object. And so this 10,000 boxes is actually one object being rotated.
You know, it's really interesting hearing you folks talk about this. I just wanted to say I'm a logo programmer from way back. And my version of logo was Atari logo, which just goes to show you how old I am. And that version of logo had DynaTurtles, exactly, where you could actually animate the turtle and move it around the screen. And it's interesting because as I was playing with VPython in preparation for making the show today, I had that kind of feeling of, like just being able to, with really simple programmatic statements, box, sphere, et cetera, I was able to pop 3D objects up all over the screen to do my bidding. And I really, one of the things that occurred to me as I was sitting there playing with this is, wow, if I can, manage to get the 5 seconds to rub together, I think it would be really cool to write a 3D squirrel using cubes with this thing. Because anybody who remembers logo remembers that squirrels were always one of the big examples they taught you how to make. So it's really nifty that you folks thought through making this, giving this the immediacy, you know what I mean? Of you can type simple invocations and get simple but really satisfying results that look good and that look like what you think they should look like immediately. I think that kind of the quick positive feedback is so critical for driving adoption in technology.
I think box, left parens, right parens is a lot nicer way to start learning about how to write computer programs than printing hello world.
Yeah, it's definitely a much more visceral and impactful experience than just seeing a computer print something out to the screen. And it's also a lot more impressive, particularly for people who have become used to the capabilities of modern computers. And, maybe 30 years ago, Hello World was a novelty and, worth calling somebody over to take a look at. But these days it's, whatever.
Not so exciting right now.
Right.
Yeah, that's a big piece of it. It's visually, you can make something fairly easily that's visually engaging, and it actually can be visually engaging on its own or because it's the output of a scientific model that you've created. So you're actually seeing how your model of a system would behave, and you're able to compare it to the behavior of a real system.
Actually, it strikes me, since you were talking also about the integration between VPython and Jupyter Notebook, I would think that VPython could be a really nifty data visualization tool, right? I was thinking in terms of using some of these primitives to make some really effective and mind-blowingly cool-looking graphs for some of your data sets. That could be really neat.
Yeah, and not just... And I think some of our colleagues who are computational physicists actually do use it for that. And an interesting thing about it is that you can go beyond graphs and do volume representations, or the fact that you can do it easily in 3D, I think is a big plus, and that it can be dynamic.
And they can run on your friend's phone when you send them a link.
Well, some of these things might not run on my phone.
I suppose it depends on if you've got the latest and greatest phone, and if not, then tell them to go out and upgrade.
I have to say, though, I share your enthusiasm for the fact, those of us who are old enough to remember when computers were something that, you loaded the data off cassettes and it took, half an hour or 40 minutes to get anything going. Having this device that you can pull out of your pocket or out of your book bag that is totally self-contained and has the ability to create, eye-popping 3D visualizations interactively, that's miraculous. It actually, talking about this and Jupyter Notebook and things like that, it makes me hearken back to a cartoon that was popular when I was a kid, Tennessee Tuxedo, with Mr. Whoopi and his 3D blackboard, 3D BB. That's kind of what I think of these days, because it's you can these tablets you can do so much with. I mean, the computational power in these things is mind-boggling, and for those of us who remember, it's all the more miraculous.
Yeah, I started out with punch cards and teletype output, so we've come a long ways, and it's great. I mean, this is so much more interesting, and it's so you can see the results of what you're thinking so rapidly, and change it and try it again. So exploration of model spaces is so much easier.
A very small comment, which you might want to delete because it's not that important, but I'll just mention that the GlowScript version of VPython has had an interesting, important impact in that often in many kinds of educational settings, especially pre-college, the IT department will not install Python on school computers because it's open source and that's known to be very dangerous. Well, they actually sort of can't not let you use browsers. And so some people interested in our work who are teaching at high school level or even earlier are very pleased that they can write and run VPython programs on their Chromebooks, which the schools have and are very inexpensive, whereas they could never possibly actually use standard Python.
The fact that there's nothing to install for the GlowScript version also means that the barrier to getting started is very low.
Absolutely. I mean, when you think about sort of walking a computer novice through, and things like Anaconda make it an awful lot easier, but walking them through the process of installing Python and all the necessary dependencies, having something that's browser accessible makes all the difference in the world.
Absolutely. Absolutely. It really lowers the barrier to getting started.
So, is there anything that we didn't cover that you think we should have, or anything else that you want to bring up before we move on?
I don't think so. You've asked good questions.
Thank you. Appreciate that. We try. For anybody who wants to keep in touch with you guys or follow what you're up to, what would be the best way for them to do that?
Well, there's the VPython forum. There's a Google forum. There's also a GlowScript forum at the moment for historical reasons. Probably those two forums in the not distant future will merge into one VPython forum. So that's a good place to go. We'll give you our picks are going to be URLs to our work,
okay,
both physics and computers. So that those offer contact mechanisms also.
Okay.
A lot of our the major projects, the classic VPython, GlowScript VPython, and Jupyter VPython are all in GitHub, of course.
All right. Well, I guess with that, we'll move it on to the picks then. So I'll start us off. And for my pick today, I'm going to choose a book that I just started reading a couple of days ago on the train called Land of Lisp. And it's actually very enjoyable. The author does a really good job of introducing a lot of humor to the narrative to keep you interested in learning some of the principles of Lisp, and there are a lot of very amusing illustrations throughout. So it's a much different take on a technical book than I've read in a while, and I've been thoroughly enjoying it, and it really makes it flow a lot better than some of the more dry technical treatises that I've read recently. So definitely recommend checking that out for anybody who has even a tangential interest in Lisp. And with that, I will pass it to you, Chris.
For my first pick this week, I'm going to pick a TV show. The Sci-Fi Channel, as I mentioned in a previous pick, after producing like nothing but utter dreck since they came on the air, has all of a sudden somehow gotten a budget or a clue or something, because they've produced not one but two shows that I really like. I already picked the first one in a previous week, The Expanse, and this week I'm going to pick another one called The Magicians. I was really, once again, very surprised at this. I was expecting it to be really horrific, quite frankly, but it wasn't. They seem to really have actually, spent some money on special effects, and the writing is pretty good. It's entertaining, it's interesting, and I definitely am looking forward to seeing more. My next pick is Swift, the Apple programming language for writing iOS and Mac OS X applications. I just want to pick the language itself because I have always found Objective-C to be kind of intimidating. I'll admit it. I've used C and C++ in the past, and they I can do it, but it's not necessarily my favorite place to live. And Swift is just at a level of abstraction that my brain is more comfortable sort of living in, and I've really kind of appreciated that, and it's allowed me to sort of make inroads into building iOS and Mac OS X applications, which is great because I've been an enormous Apple fanboy for years and years. As Tobias can attest, we've had a number of Linux Mac conversations. So yeah, I'm definitely loving that. And for my third and final pick, I'm going to pick Atari logo. I realize this is kind of a silly thing to pick because it's a retro, tool that nobody in their right mind these days would use unless they are sort of, people who've used it in the past. But this programming language and visual programming environment is really what inspired me to get a career in computer science. It's for all the reasons that we discussed. Being able to create a turtle that looks, and change its appearance to a spaceship or, whatever, because that's where I was at that particular point in time, and have it fly around the screen and collide with and detect those collisions with other sprites, all using a really high level language that's really, really accessible, was a mind-expanding discovery for me at the time. And I think it's wonderful that some aspects of modern technology like VPython have embraced that kind of enable that kind of interactive exploration and positive feedback loop. And I'll stop there for this week. Bruce, what kind of picks do you have for us?
Well, we have three. Okay, me. All right, fine. Me. VPython.org, VPython.org. That's the sort of mothership of original classic VPython, but it now has links to other pieces. And glowscript.org. That's GLOW script. It stands silly by meaning graphics library on web. Glowscript.org, that's the place where you can register and write programs that are saved for you in the cloud. You can run them there, debug them there, export them to your own web page, or give a link to that spot in an email address to somebody and they can click on it and they're running your program. And then there is, you want to do this one?
Well, I have two. If you're interested in our physics work, or even just seeing a lot of physics demonstration programs written in VPython, Matter and Interactions, all one word, .org. So matterandinteractions.org/student will take you to a bunch of demo programs written in VPython, both from mechanics involving spaceships and balls and springs, and also electricity and magnetism fields. And since you're a logo fan, Chris, have you looked at NetLogo? It's a very interesting contemporary incarnation of logo that's used by people exploring complex systems. It's another great first language for kids learning to program, and it lets you take lots and lots of interacting things and see patterns emerge from simple rules. So that's a very cool contemporary incarnation of logo.
I have actually. I've looked at NetLogo and I played with it quite a bit, and I have to admit, and I'm totally guilty of this. I sort of got into it and thought to myself, "Ooh, it's going to have Dynaturtles, and maybe we'll do the same thing as they used to be able to do in Atari logo." And it's kind of not built for that. It's built for something totally different and even more awesome, as you say, these sort of creating these complex systems with all kinds of interacting, objects going on. But it kind of, it's a different awesome thing that I really should definitely spend some time to dig into. I have not yet, though, because like I say, I'm guilty of sort of looking at it, playing with it, it not doing what I had hoped it would do and bouncing off. So I will definitely invest some more time in that. Thank you for the suggestion.
And for anybody who's not aware, I'm sure that you all are aware of it, but there's also there is an implementation of Logo in the Python standard library. So if you import Turtle, then you can actually write Logo programming. You can write Logo programs in Python.
Well, Turtle programs.
Yes, sorry. Yep, yeah, so if you import Turtle, then you can use your Turtle to draw on the screen.
Cool.
Well, I appreciate you both taking the time out of your day to join us and tell us more about VPython. It's definitely a very interesting project, and after learning some more about it, I'm probably going to start using it as a way to get my children introduced to programming. I started using the Turtle module a little bit, but this seems like it might be an even better environment for experimentation and teaching them about Python. So thank you for that.
Let us know how that goes. A lot of people have done that with their kids and with good success. So.
All right.
Thank you for having us.
Yes, thank you very much for taking time to talk with us.